Hello, this is Junyoung Cho or Jamie Cho. This is the demonstration video for computer architecture fall of 2016. I implemented a deep neural network in synthesizable Verilog. It was synthesizable on the FPGAs, but unfortunately, due to a bug in the FPU that I used as a library, it could not compute the correct outputs. But in simulation, at least, it was able to compute the right results, so I consider this a success. In this video, I'll be going through the documentation pages and explaining in detail what I did and why I did it, those things about the project. So what I did is essentially I implemented an artificial neural network in Verilog. As a little bit of background, artificial neural networks are a recent advancement in computer science that are aimed at simulating what humans do when given like a sensory input in order to compute like a desired behavior or like an output based on that. It turns out that it's like stacks of layers of neurons that pass on their activations until it finally reaches like a highly processed sort of a feature based on the inputs, which then dictate the behaviors. And that's exactly what we're doing as well. So a neural network is actually a very highly parallelized algorithm. And well, unfortunately, CPUs are very generic. It's an extremely powerful processor, but at the same time, it is at the core of it sequential. Regardless of the number of cores that it has, it can have like dual core, quad core, octa core. It doesn't matter. At the heart of it, it's a sequential processor. And that's why people have realized maybe CPUs are not really good for this task and turned to alternatives like GPUs. People have been using CUDA for convolutional neural networks all the time. They work relatively fast, actually extremely fast, a lot faster than a CPU. Google has their own sort of processing units called the TPUs, tensor processing units, which are apparently 3 times faster than an equivalent processor. But well, recent benchmarks have actually shown that FPGAs can outperform GPUs. And what I realized when I was taking CompArch is if I can use FPGAs, which are massively parallel processing units that can do simple tasks really well, which is exactly what we want for tasks like matrix multiplication, which is at the center of a neural network. It would be a very efficient alternative to what the CPU is doing. And I was not really aware of this at the time, but Microsoft is doing a similar thing using FPGAs in the field of artificial intelligence, probably something actually very similar to what I'm doing, but better, obviously. So, well, so here's what I did, and let's get to it. So this is the diagram for my network. It takes in an input, and it goes through several stages. The layer is composed of stages as well, even though the network itself is composed of multiple layers. Within the layer is like 3 different units, which is matrix multiplication, and then adding the bias and applying the transfer function to it. And within the matrix multiplication module, there's also the multiplication and accumulation phases to it. But these will be explained in more detail later. So what I'm exactly trying to do is all of the neurons in a previous layer is in this sort of a simplified deep neural network. All of the neurons in the previous layer is connected to each of the neurons in the current layer, and the sum of all of them undergo the output of all of them is multiplied by the weight matrices that correspond to each of the connections between each of the neurons in the layers. And the output of that on the output of that, we add a bias, which helps the convergence a little bit when we are training it. because sometimes change matrix multiplications and the activations may not sufficiently be able to represent the function in a simple enough manner. So that's why we add the bias, and that value is fed into the neuron, which then activates it based on whatever activation function it may have. Here's like sort of what the activation function does. It pushes things a little bit to the extremes. In this case, between 0 and 1. So if something is closer to 1, like 0.9, it will be a little closer than 0.9 after the sigmoid is applied, which is my activation function. It's going to be like 0.93 or something like that. I don't exactly know, but it essentially makes things a little more exaggerated, which is what it's doing. So this is what a neural network does. And the process itself is essentially just matrix multiplication and some like logarithmic functions, but we're just approximating that. So let's get to how we do matrix multiplication in Verilog. So what we do is store the intermediate results because we can't just overwrite them. It's not an atomic operation, so we need to store like an intermediate array and then accumulate all of them. The simplest way to do it would be to just add a plus b plus c plus d, but that has the time complexity of O n, which is not ideal, and we do not want to do that. Since we are taking advantage of the parallel capabilities of the FPGA and Verilog and all of those things. So a better arrangement would be something like of log n, where we are adding the intermediate results of a plus b plus c plus d, so that they're grouped together, which boils the time complexity down to O of log n, or log 2 of n, which is a lot better. Actually, this idea comes from CUDA, or like GPU sort of parallel computing paradigms. It's a very classical sort of reduction operation, and well, I felt like it's worth saying that it came from a similar field of parallel computing on a GPU, not an FPGA, but essentially the same idea. And the following figure, which you can see in more detail here, they're broken down into units of 8 characters because they're 32-bit hexadecimal, but it's pretty obvious. So like A corresponds to W and B corresponds to I, but what's most important is the output of the two. And you can see that in the matrix multiplied results, they're actually very similar. BF4C2 E88, BF4C2 E88. There's like small sort of differences, like in here it's like 3DA5E2E4, here's 3DA5E2E5. They're like sort of rounding differences, but you can see that the matrix multiplication module is working as intended. And after matrix multiplication, it's just vector sum, which is very easy. It's just addition module from the FPU multiplied or like applied to multiple different inputs at the same time. So it's simultaneous. And then after the addition is obviously the activation part, which is essential to make it non-linear, because if you're just chaining different matrix multiplications together, it can never compute something that is nonlinear, as opposed to when you have these things like a sigmoid or like a hyperbolic tangent, which I've already shown you looks like this. It's very clearly not linear, and it helps the network be able to approximate the function better. It also needs to be differentiable. This is not really relevant to what we're doing because we're just doing a feed-forward neural network, but when we're computing the back propagation of it, we need to compute the gradients and apply the gradients to all of the responsible neurons from the previous layers and stuff like that. It's not really important to us, but in general, the activation functions should be differentiable and they should be nonlinear, which is what we're doing as well. it's kind of similar to what why we need an extended Calvin filter as opposed to just a Calvin filter when we're dealing with nonlinear functions. As I said, I should have chosen the FPU a little more wisely, because the specifically one that I've been using did not support a wide range of things, including the exponential function. I couldn't compute the actual sigmoid function, which is given by 1 over 1 plus e to the negative x. And therefore I had to use a very closely similar sort of approximation, which is 1/2 times 1 plus x over 1 plus the absolute value of x. And when you actually look at the graphs, it's pretty similar within the domains of like sort of a small number, and it's reasonably close enough so that the network will be able to train from it. One sort of gotcha is that you cannot use the weights from weights that have been trained with one activation function, even if it's an approximation of the sigmoid, to another network that has another activation function like a sigmoid, because that's going to give you a drastically different result, because the sigmoid is, and in general all sort of activation functions are very very sensitive to it, small changes in the input. And if you want to run this, you can just run the approx sigmoid.py from the GitHub repository after you clone it. You have to specify an argument called plot in order to plot the results, but that should be pretty obvious. Well, actually, if you look at the waveforms, you can see that well, so like this is the clock, and it finally finishes after it computes the value of the y. This is the propagation path. So first of all, it computes the x, and this is 1 plus the absolute value of x, which is abbreviated to OPEX. And xdo is x divided by that result, which is computed here, and it takes quite a bit of time for division, which is kind of expected because it's a more complicated operation than just just a multiplication or an addition. After that, we add 0.5 to it as shown in the equation, this is abbreviated, but we're actually adding 0.5 to it because we expand it. After all that finishes, like, it's broken up into stages, obviously, which we can also see here. It emits the done flag, and well, when it's done, we can sort of see what the output is, which is 3DD5555C. That corresponds to C073333 3. All these hexadecimal numbers would probably not make a lot of sense, but here, if you look at the so I wrote a little bit of a conversion sort of script that's gonna convert hexadecimal to floating point number, and what this is saying is that the sigmoid applied to negative 3.8 as input will output 0.10, which should make sense because the sigmoid caps all of the inputs within the bounds of 0 and 1, and because it's very negative, it's gonna be very close to 0, as you see from the function here. So like negative 3.8 should be right around 0.1 as what we have seen here. And when we actually run the script and ask for the value that's going to be obtained by negative 3.8, you're actually going to get that exact number. So we know also that the sigmoid module is working as intended. The sigmoid module is actually vectorized, which means that if it gives you only one number, it's going to only output the sigmoid of that 132-bit number. If you give it two of them as a vector, it's also going to be able to compute the sigmoid of the vector of it, which is very convenient. This is mostly because I set them as parameters, as I did for essentially all of my modules. They're all parameterized so that the network itself is very generic. it can compute the results for any given number of inputs, any given number of hidden neurons, any given number of hidden layers, any given number of output neurons as well, which is a very generic interface to a relatively simple, admittedly simple neural network. So after we have both of those modules and a fair bit of just small gotchas and small modules, we essentially have our network, because a layer is just, as we said, a chained operation of matrix multiplication and bias and applying the activation to that. And well, let's just cut to the chase, right? So my network topology is 2 input neurons, 4 hidden neurons, and 1 output neuron, which is like, well, it's an XOR, so it only has to output 1. But like in other scenarios, it would obviously be able to output more than just 1. But this is the network architecture, and well, let's just look at the results. So the output in hexadecimal for the XOR of 0 and 0, we know for a fact that it should give you 0, just like XOR of 1 and 1 are supposed to give you a 0. And the output from the neural network is going to give you 0.09, and this is because the network itself is a floating point network, and it's an approximation of that. If you threshold that with 0.5, you're going to get 0, 1, 1, and 0, and it's actually very close to its extremes, which gives us the confidence that the network is working as intended. And this is actually the exact output you'll get from the network, from the separate network implementation that I've created, which you can actually find in one of the documentation pages. Well, the waveform for this is actually like maybe it's not very complicated, and maybe it's not really important to see this. That is because like it's broken down into submodules, and we've already seen what these are going to look like. And this is just a top level module that's going to be encapsulate all of that information and all of the process into like several small stages, layer 1 and layer 2, and when it's done, it's going to give you the XOR of that 3DBD05B0, which is actually what you see here, the XOR output for 0 and 0, which is 0. And when you convert that into a floating point number, you're going to get 0.09, reasonably close to 0. So let's talk about what this project implies, what the significance of it is, and how you build it and build on top of this. So you can just simply run the makefile in the root directory. If you go to the project directory and just run make, then you can just make all of the object files that you need in and all of the executables, and just run it and see that it's computing the right things. You can see here that the output of the network is exactly the same as what's given in the table, because there's really no sort of random variables or like time different things involved in here. If you run it, only just like run everything and see all the VCDs, then you can just say make run and verify the outputs that way as well. And obviously my implementation has a lot of limitations. I couldn't implement a full convolutional neural network. I couldn't test it. This is because its compilation time was way too long. So here you can see the plot between like the compilation time and versus the size of the input vector, and because for a deep neural network, it's actually going to be let's say it's a deep neural network with the architecture or the topology of 784 input neurons and let's say 48 hidden neurons with only 1 hidden layer, it's going to give you the probability distribution over 10 different digits, which is going to give us 10 output neurons, right? But even that gives you 784 times 48, which is a massive number of connections, and that just blows up the compilation time, which made it kind of impractical to do. Well, obviously, it was very impractical to do a convolutional neural network, but even for a reasonably deep neural network with reasonable number of hidden neurons, we couldn't really test it for MNIST data, which was the original intent for a digit classifier with the FPGA, which is why we settled with an XOR. It turns out that the empirically determined compilation time was O of n squared, which was like, kind of unacceptable within the time frame given, and the resources that my computer had. It just couldn't compile it. Anyways, if you want to verify the results, there's also a separate backpropagation network in Armadillo that I implemented. Its links are also in GitHub, in the links in the documentation, which is supposed to compute the exact same weights as a result of its training over time, which is going to give you a little bit of confidence that the neural network is doing what it's supposed to do. So, what are some of its next steps? It's not very robust, as you can see. Like, I was not able to really get it working on the FPGA before the break began. And I think one of the reasons is because the FPU was not synthesizing friendly. It had gated clocks everywhere. When I saw what it was doing, it was using flags and writing some of them simultaneously. I had come to this realization way too late in the project to fix an FPU, much less that I didn't exactly know how it was implemented. And it was way too late to change the entire network architecture, so I had to stick with the working simulation and non-working FPGA. Well, probably in the future I'll try to change that as well. The network is not trainable, which means it's not a backpropagation network. It's only a feed-forward, which means it can only be used but not trained, which is a great pitfall. And I would this is some of the things that should and could be improved on this. Although this would obviously entail a lot of complexity. And pipelining. So like there are three things that should and can be done with the network. One of which is backpropagation. The other one is convolution, and finally pipelining, in order to speed up the process. But if you want to implement pipelining, obviously you want to do other things like mini-batch learning, so that it's going to do things in parallel as opposed to just doing things for like one input at a time, even though you have a pipeline. So it has to be optimized for that kind of purpose as well. Fortunately, it's a very strong paradigm to do a mini-batch learning on a neural network. So there is a strong benefit to doing a pipelined neural network. But this would obviously imply that there should be heavy modifications to the network architecture. So I think this is a relatively thorough overview of what I did. Mostly because the documentation page contains most of the information. I was only going through them in the video. Thank you for what you've done this semester, although the semester is over, and have a nice break.